Welcome everyone. Good evening. I think. Sorry for a few minutes. We are trying to set up so that we can do the recording. It's a pleasure to kind of have Prashant Goswami here, giving us one of the few talks that we have in graphics in this department. This is a very interesting area that he is working in. So Prashant is visiting from Sweden. So he's a faculty at BTH. Prashant finished his bachelor's and master's from IT Delhi. Then he went to Zurich for his PhD. He worked with Renato Pajarola, a good friend of mine who's also visited us and has given very interesting talks on visualization. Prashant then went on to do postdocs in Singapore at NTU and then at Indria Grenoble. I understand from today's conversation that he also had a stint in industry, although that was not in graphics. And he's been at BTH for close to a decade now.
Yes.
Right. So it's great to have him visit us and give this talk. I think he's visiting for the day. So after the talk, if you would like to come up and chat with him about your interests, feel free to do that. But on to the talk today. For the topic for his talk is snow and cloud, and which is always kind of interesting and cool to see. So look forward to your talk, Prashant.
Thank you very much, Vijay, for the nice introduction. And it's a privilege for me to come over to IISc and give this talk. I never thought that even like 3 weeks ago. I randomly dropped an email to Vijay and he very quickly get this organized. So a lot of thanks to Vijay for this. And I think Vijay has given an excellent introduction about me. So I will not delve deeper into many aspects, but I started at BTH as an assistant professor, a permanent assistant professor, and I got rehabilitation, which is existing in German, French, and even Swedish systems. It's called docent in 2021. That makes you equivalent to an associate professor. And last month, or maybe this month, I got promoted to Bitrande professor, which is also associate professor, but it's an incremental position. So that was for my journey, and I'm looking forward to becoming a professor in a few years. Let's see how life treats me till then. But coming back to my work, I will just quickly summarize what I teach at BTH to just reflect on how different the topics that we teach in India and US are from in Sweden or maybe in Scandinavia also. So I teach a course on game engine architecture, and I am the examiner and a supervisor for many supervisions, bachelor's, master's, and dual degree. We have a dual degree program in game engineering in BTH, which is very popular. And I'm also teaching research methodology course. I'm pretty sure most of you don't have heard about any course like that here. Even I hadn't till I started in Sweden. And in the past, I have also taught applied artificial intelligence and game artificial intelligence, and this list will change with time. So to begin with my research interest, when I was at Zurich, I was working on the more common things that were around at that time. That includes terrain rendering and simplification and point-based simplification. So that you see a St. Matthew statue there with more than 300 million points that is rendered on 10 computers at the same time. So that's not only that we had our own simplification algorithm, we also did parallel rendering of that thing, and it was pretty. I was happy that we did it. And then when I was at NTU Singapore, we did some work on geometrical processing. It's something called reciprocal frame structures. It's been like more than a decade, so I will not probably talk so much about it. But something that stuck with me all throughout were two things. First of all, GPU-based computation. I've always been working on GPU-based computation. And second thing is some kind of fluids, whether it's water or it's snow or it's clouds. I've always been interested in this. So I started with water. Then at India, I picked up clouds, and now I'm working on snow. So that's why this particular talk would be about the interest that suits me the most. And not that I'm not willing to experiment with other things, but this is something that I'm really happy to share with you. So I don't know how many of you have played computer games. I think quite a few of you. And if you've played computer games, then you would have seen that they have several settings. Recently, there have been some games, and as you can see, Red Dead Redemption, if some of you have played or at least heard that name, that are based in snow settings, right? But the problem is that if you look at the existing SDKs, NVIDIA SDK, yeah, then it has a lot of materials. It has water, it has cloth, it has deformable objects and all, but it doesn't have snow. Yes, and that there's a reason for it. How do these games manage? These games do not use physics for snow. The reason is that it's so complicated in real time to simulate snow. Yes, so they use a mesh and they deform the mesh to give it the impression that snow is actually the material there, but it's only a two-dimensional thing that's being deformed. Yes. So now that gives you some idea of that real-time solution for snow in computer graphics is quite far-fetched a few years ago, at least. So what we worked on is towards designing or creating an efficient solution for snow that could be a good suit in computer graphics, right? Because the requirements differ from agricultural science or civil science, civil engineering, something like that. So only two prior works existed while we worked on this. There was a SIGGRAPH paper in 2013 by Disney Research and another university collaboration. That was this material point method. Has been known for long, but adapted for a good use in computer graphics. It was an excellent paper, but it was anything but real time, right? It was purely offline and it was reasonably slow, quite slow. Then there's a group in Freiburg, Germany, Matthias Teschner's group. That is a very popular group on particle-based methods. So they published a SIGGRAPH paper on snow. That's the second one in 2020. And they have an existing solver that's called implicit incompressible SPH solver, smooth particle hydrodynamic solver. So that solver was adapted to incorporate snow. And it also had a lot of advantages. You could see that this was also a good work, but it was also not real time. It was purely offline and on CPU, and it took a lot of time to complete one time step of computation. So now,
So when you say snow, do you specifically saying snow represented as a particle system, or talking about just the final effect?
yes, final effect. Snow as a material. So all the models that we take up don't matter as long as the results look suitable for that particular, like let's say CG. So they have used different methods. The first method was semi-Lagrangian, which means grid-based method. The second, first one, this was with grids, with some particles, and this was purely particle-based. But they both tried to do the same thing. You had a question? Okay, so what we did, we took another model that's called discrete element model. So far you have heard Eulerian, semi-Lagrangian, which is grid-based particle, and Lagrangian, which is purely particle, SPH-based. I know these terms might sound like a little complicated, but you don't have to think too much. Just go with the flow. You will discover everything. Yes, so we took another model that's called discrete element model, DEM model, and it's completely CUDA based. So first SPH solver that was CUDA based, completely GPU based, 2019 already. So what we did was that we said, okay, let's have all distributions of particles. Let's start with a big snow particle with a lot of air inside it. Yes, and as it gets squeezed, air leaves the particle and it becomes ice eventually. Yes, so those are the two extremes. So our simulation will contain those both kind of particles and everything in between. Right. The advantage with this is that if you know eta, and eta is only dependent on the radius, right? Because the state of a particle is only dependent on the radius. If you know eta, you can interpolate and find out all the physical properties of any intermediate particle. Yes, like Young modulus, cohesion strength. So you don't have to really work too much on having different physical properties or different, complications. You can just adopt that simple model. Yes, and then all particles are allowed in the simulation and allowed to compress and change their form and transform. But there were other things also needed. So snow has a very interesting behavior. Two particles that are overlapping each other, they repel each other. That is very common with water also, with a lot of other materials also. But the other interesting part of behavior is that if they are in vicinity of each other, not too far away, they will attract each other. Right? So both of those behaviors need to be captured. And then we took some inspiration from the base models that were working in purely snow-based modeling, not so much on computer graphics. and we took their adaptation, took their model and adapted it to provide some normal forces. So these are normal forces, right? And as you know, in nature, there's always a friction, right? So in these particles also there is a friction, and you will see that the tangential forces are also acting there. Yes. So now put it all together, but little bit more things. So that was all the the advantage with this method. Now you have all the forces. Now start compressing the particles, right? So you can compress a particle only when a force and an equivalent opposite force is available, right? So whichever is minimum will be used for compression. Yes. And finally, one very important thing which none of these methods had is the bond behavior. You know, unlike if you look at that image, and if you drop snowball, and if you don't have the bond behavior, it'll all come back, right? In the real life, if you drop it, it should actually split and not come back. That means that you need to mark particles that have broken bonds so that they don't get into the attractive forces again, the same forces that we discussed. So now we put it all together, yes, and now we have an eye system that works very efficiently, very fast. It's not the visually the best system. It was a journey, that started us into an efficient snow simulation. So now we'll look at this video. So you see a tall column of snow particles that are being compressed under their own weight. And the darker the particles are, the more of ice they are on the downside here. That was published in EGPGV, Geographic Symposium on Pyrographic and Visualization in 2019.
Darker how?
So these particles, you see that the ice particles were actually, I drew it black for visualization. So that's no visualization problem. So I visualize them as in a darker color to show that actually they are ice now.
Oh, so it's not the shading, it's just
But they also have a smaller size.
okay.
And now when you put the surface on top of it, this is how it looks. Does it look a little bit like snow? I asked a Siberian teacher who works at BTH, and she said that, snow, when you leave it for a very long time, will get this behavior. Like if you leave it for weeks in Siberia, for example, where it doesn't melt so easily. Then maybe I can show you a lot of, so more than 100,000 particles, as you add more and more snow objects one on top of each other. But one thing you might have realized is that you need a very good resolution to capture high quality snow simulation, right? So even though if this method had some real-time aspects for less particle counts, it still needed improvement in terms of running time also, because so you can have more particles. The more the particles, the better is the quality simulation, invariably in all simulations. Okay, and that brings us, so they say that you need to go further and improve your existing method. That's what we did in 2022. That was the same conference, and this paper got very high reviews. So there were two big problems with the earlier method. First of all, it had some stability issues. There were particles popping out, and it didn't behave as it should be behaving all the time. Partly also because boundary was not handled properly. Secondly, it had a very small time step. You know what a time step is? When you integrate the particle, so new position is equal to old position into velocity into delta t, right? That delta t is a time step. And the old method needs to have a low time step for stability reasons, right? So what we did was to work in this direction to improve this method. There was a paper in 2009, predictive corrective incompressible SPH. Yes, that was also from my group in Zurich. So that inspired me to go further and fix this method. You take the same forces, you take all the same bonds and compression and put it in an iterative loop. Yes. So you let particles get into good positions and good configurations with each other as you iterate one time, two times, three times within a loop, right? So you can, with that, the invariant is that you have to minimize the overlapping error, which means that the particles should not overlap each other, because otherwise it's not physical. Physically, that's not how they are. And the benefit is that you can have more behaviors of ice, with some settings of variables. You can change it to wet and to incorporate wet and dry snow behaviors. And you also sample, objects like these and the ground, you can sample them as static particles. That really improves the stability part. So a lot of instability in simulation comes from the boundary, right? So if you have boundaries sampled as some particles, that really improves the stability part. So, and some graphs for you to see that the errors were pretty reasonable. They were, well, for a large time step, we had time steps that were almost 10 times larger. Instead of 0.1 millisecond, 1 millisecond. So if you are developing some games, you know that 1 millisecond is an acceptable time step for games, yes? And it produced results that could be up to 8.66 times faster than the previous method, our own method, yes?
How is the error?
So the amount of overlapping that you allow between any two particles.
There should not be
Any overlap, exactly. So you can probably achieve it, but then it'll be very expensive. So we just usually say that 1%, 2%, 5% error. And computer games, that's good enough. And this was very stable. So if you look at the previous method, the one that I just introduced to you before, this block actually became this, if you left it like that. This is not really how it should be, yes? But with the new method, it actually remained like this. This is how it should be. So the stability was also improved. And we did a user study. So in Sweden, at least our group is known for doing user studies. I don't know if you do user studies. Do you?
Not so much.
Okay, good.
We do case studies with experts.
Okay. But I was not also into user studies. But after I started at BTH, I got used to the idea of user studies. So we did some user study to see if people felt that the material resembled like snow, and the results were positive.
Anything like a actual snow grapher or videograph it with some high resolution camera and try to simulate the same thing.
That's where we are now moving towards. One of the properties of many graph papers is that they show something like that. They show some validation that is close to real life. So now there's a guy who worked for NASA who sits in front of my office. Now we are working on a new model of snow physics, and he has a completely new view of this that didn't exist in computer graphics. Let's see if it works. Then we will validate it. Because he feels that the way we capture forces is completely wrong. We shouldn't be having many of these forces. But I don't know. But we can have that discussion continuing. So you see that we got, for 1 million particles, we got a speed up of 8.66 times. And the simulation looks a little improved. If you have more particles, you should have more speed up. For 2 million, the speed up should be even higher. And we had a lot of particles that could fit inside the GPU memory because it's a completely GPU-based method. Okay, let me show you this video. So now we will change the type of snow and the type of surface. And you will see how things change. With high friction, it sticks more, right? And with low friction, it doesn't stick so much. I will quickly.
I assume all these variables just change the
Yes.
behavior, particle behavior.
Exactly. And the funny part is that if you look at the other two graph papers that I showed, I listed, they also use some equivalent of these variables. That's the computer graphics hack of actual life snow simulation. Because if you take the actual variables, it will be much lower time steps and much more expensive to simulate snow. So you see the wet snow is actually kind of looks wet, yes?
The geometry of each of your particles.
It's a simple particle.
Okay.
Yes, with a radius with
Something.
Yeah, you can call it a sphere actually, because it has an overlap as
Yeah.
well.
So your overlap is identified by us.
Yes, exactly. Because that's the most symmetrical shape to handle.
Yeah. there any environmental variables?
Temperature.
So is that a fixed temperature?
In the previous paper, actually, we changed the temperature and showed that it could melt or freeze again, or so that part we left behind because we felt that that's the obvious thing. We should not worry too much about that. But the framework handles temperature and also handles a little bit of air force, buoyant force. So because when you have like pure snow, which is scattered around, the the buoyancy force becomes important too. But this is cool, right? You can push it all the way to the ice actually. Now this is ice.
So wouldn't that also change the local temperature?
Yes.
Corresponding local.
Of the of
For example, maybe not that in the earlier example where you had the snow packing, the temperature rise.
right. I mean normally it might be, sure, depends on the situation. And normally zero is the point where freezing begins to happen. Anything below that, it might change the constitution of ice, but it's possible to handle it. We can handle it. It's there in the framework, but we didn't bring it further in this paper. So this is an interesting case because this is how you would like the snow in computer games to be, right? In a scenario like this. And still the video is about 3 times accelerated here. Now what you will see is how does it look in real time. This is real time. It's happening as it's computing. So this is the fastest existing snow simulator as of now, and we are working to make it even faster. It can be done by tuning these parameters. Flowing snow, rigid snow, CUDA. I have to check, but I knew when I was working on the paper. It's in the
system like consumer grade or
yes, it's
high end.
no, it's not very high end. It's not like the very expensive graphics card. It's the medium one. It's for I think it's for development, but not the game playing and not the $4,000 ones. No,
Yeah.
no, not those ones. Yes, I can. It's in the paper. I can check and let you know. At one point of time, I knew all the names by heart, but now you see, I'm more interested in other things. So this is 120K particles, and you see that there's two-way coupling. It's how snow interacts with the matter and how matter interacts with the snow. Both those forces are put together. This is quark, but if you throw a watermelon, it will have a higher impact, right? And it'll go further. And if you throw gold, it should go even further.
How does the material affect? Is it the friction?
So it's both the ways force. There's also this repulsive force between the material, and there's a force that comes with the gravity and with the weight of the material. So you put it all together, and then you get the total force. I will show you. Okay, maybe yeah.
Yeah, I'm thinking about this in terms of like engine integration. So is this like a custom render that you built, or have you integrated this into something like Unity?
It can be integrated in Unity, but then I think the rendering overhead might have to be looked into. Right now we use NVIDIA Flex.
Oh, okay, so you're using your own implementation.
Yes, exactly.
Well, I mean, I guess one difficulty I foresee then is that it's difficult to then integrate into like actual larger projects.
Right. That's why there's only one SDK by NVIDIA, right? That is doing a lot of things in physics, and they had to write their own SDK. But I don't think it's that hard to implement to integrate this one into that because it's already using NVIDIA Flex. But yes, but that would be one of the things in our head for later on that we have to use Unity and showcase this at some point of time, the improved version maybe.
Yeah, because if you're relying, so that means that the physics solvers, and I mean, solver here relies on NVIDIA's whatever APK. Right?
No, it's only for the rendering.
Oh, okay.
NVIDIA Flex is only taking care. I have to show this a little bit more. So this is a good case, 1 million particles and about 300,000 boundary particles of the hut. And they are sampled, so it's about 1.3 million particles. It is 20 FPS, but it is speeded up 16 times, right? But this is only how efficient you could get with snow as of now. And NVIDIA Flex is only used for rendering, so the rest is our engine. Do you think that the second method looks better than the first one? We are all unanimous on that, yes. So that was published in EGPGV also. Then last year we had implemented an improvement, or let's say an adaptation of this second method by bringing in some spatio-temporal adaptivity, which means that there are regions that are not important. Then make them large in particles, give them large particle sizes. And then there are regions that are not moving at all. Why should we have physics on them in every frame? Can we skip it for 1, 2, 3 frames? Yes, that is the idea, spatial temporal activity. This was published in ACM, it was last time ACM, but proceedings of high performance graphics last year. And I will probably not discuss the loop because it's intuitive. As I said, you just apply both the adaptivities and get the speed up. So what is the speed up that we get? So the last method got 8.66 times speed up, and this one is about 3.5 times faster than that method. Right? And of course, it has its own negative points that I will show you now in the video. I think this would be here. You can see that. Do you see a difference in the quality when that one is including both spatial and temporal adaptation? And that's the base one. That is the one that we discussed just now before this. Do you see a difference in the quality? There is, right? And that is the trade-off. It's always like that. There's always some trade-off, yes? Especially with simulations. If you change particle sizes, you get into trouble in one way or the other. So here is the splitting process. And then the merging process. So the merging takes some time. Usually you give a time of like 100 frames, 100 physics steps before, it slowly gets merged or it slowly gets split. Two particles. So they slowly have to reduce the particle count, right? So you pick up two right particles, merge them, then you pick up another two particles and merge them. You do that in parallel, basically. And similarly for splitting the particles.
So the splitting and melting, does this assume something about the underlying SPH that is going to be used for the rendering?
So what it tries to do is to find best fits. So two particles that are going to be merged, they should be as similar as possible in size, in compression level, other attributes. For splitting, that is not a problem. So yeah, that is true. We have to see that two particles that are going to be merged are as similar as possible. If not, then we actually merge them anyway.
Did you create a new particle every time you there?
Yes, instead of the two. So we delete the old two and we create one.
Oh.
Or you just keep one of those and delete the other one. But you see now the impact is clear, right? So in cases where there's micro interaction with the geometry, that is problematic. But if you zoom out, then things become better, more tolerable for the game industry.
So does this naturally integrate with maybe I missed it, but this integrates, this is layered below the SPH.
No, we are using DEM, discrete element method.
Or directly on.
It has few advantages and of course maybe disadvantages. The advantage is that it has a lower neighborhood size and the force computation loop is much simpler, so much inexpensive as compared to SPH. SPH has this kernel, weighting kernel, which is very, let's say, time consuming. You have to first compute the density, then the force, then other forces.
But for the DEM, this will have
but
on the sample.
there are no kernels, so it's only distance based, and that size of neighborhood is very little as compared to SPH. and there you compute only one forces only once. You don't have to
No, but
compute.
your linear resolution, is that fixed?
Yes. So they are discrete levels. So all the previous two works are all working on this red level,
Okay.
and here we have allowed it to go further. But I think this is more like visualization, right? Different colors. This is what I really like. Okay, and finally, last year we had a state-of-the-art report in. I had a state-of-the-art report in neurographics that was on snow and ice animation methods in computer graphics. So far we have done this much on snow. We would be very interested if someone would be, would like to extend this work with us further, or something that is of a different, from a different aspect but connected in some way. I will spend some more minutes to talk about the clouds that we have worked on. And I picked up the interest in clouds from Indira Grenoble when I was doing my postdoc. Fabrice Nere was my supervisor, and he was interested in clouds. And I was working on fluids. So now clouds are important for virtual simulators, for other applications for virtual reality games also. Yes, but one of the big problem with clouds is that if you take up any region, right? So it's like what few kilometers, and then it's also a few kilometers above. So just imagine the amount of sampling you have to do, basically, amount of memory, amount of computation, and all that for computing something in computer games. That's like an overkill. Yes, that's not required. And so computer graphics has been going the same way for a very long time. So you do a lot of processing, but you get a small cloud in the end, right? For one frame. And then you have to regenerate the same cloud for animation purposes. So this was a problem for a long time in computer graphics. And what we did in this work was to disentangle the physics and the visualization part. So what we do is that you pick up a few of those parcels, 20, 30, 40 parcels, right? And then we compute the physics variables, one set for each parcel. That means there are only 30 or 40 of those variable sets to be computed. Yes. And then once you have done that, based on the values, you try to create some noise inside each parcel that resembles the physics values. Yes. You know, a hypertexture, basically hypertexture is noise. So it's exactly what we use in this case. And you know that clouds are formed only when the water vapor condenses, right? So it's the condensed water vapor that is important for visualization of cloud. The rest is only important for physics. Yes. So what matters to the viewer is what percentage of the cloud is condensed. The more it's condensed, the darker it appears. Yes. So that's the thing that we have used here. That really reduced the physics computation time, and it gave us a lot of freedom on how to handle the visualization. Okay, this is boring. Let's look at the video. So here's one parcel that rises and condenses, but the mixing is disabled. That means that the variables will not mix with the environment around. So it will just keep on going up and down, right? It will never die. But if you allow mixing, then, it will rise up, but slowly it will lose its heat and it will lose its content, water vapor content, and it will die. Boring part. Okay, so the advantage with this method was the software or tool that allows you to change the temperature profile of the atmosphere and see what does the cloud profile look like. So you see that if you have this temperature profile, if you have this temperature profile, no clouds were formed, right? But when you change that temperature profile, the clouds were formed. It's because sometimes when you feel very humid, it's a very humid day, but no clouds are formed. It's for that reason that these all have to follow some certain temperature profile for cloud formation.
Y-axis is the height.
Yes, right. And there are other variables like relative humidity and absolute humidity and all those things. The height at which you would like to have the condensation. So this one changes the height at which you would like to have the condensation. And normally, I mean, so there were a lot of papers by one group after this that have really taken it quite further than we have. Hedrick, I think it's called. And they have a lot of SIGGRAPH papers, one after the other.
So this is all rendered on like a quad or
It's rendered on any normal graphics card where you have fragment shaders.
not. No, I
Hmm.
meant is like what's the surface that you're rendering it on?
So it's not a surface, it's a volumetric noise.
So it's a volume.
Yes, volumetric noise, hypertexture. So you create hypertexture and then you shoot rays and you collect the densities.
Got it. Oh, but okay.
Hmm. And continuing with this work, there were other things, but I'll just show you one in particular. Now we are using machine learning and everything, right? So we also tried machine learning on clouds. So this one, what this work does is that it just takes videos, a set of videos, and tries to study which are captured by users of sky with a static camera with nothing hidden, with a clear background, and then try to see, learn that pattern using GANs, DC GANs, yes, and then generate the animations. There is some more, there are some more things involved here. You have to plug it in, in our renderer so that 2D becomes 3D because you're learning only 2D images from videos, yes? You have to convert them into 3D videos. So the left is the physics one and the right is the machine learning one. And the same thing with low cloud coverage. It takes some time to. But I mean, the idea was to show that, so there's no physics at all here. Yeah. So I published another paper that I didn't cover here. It was about how to take a cloud map and convert it into 3D clouds. So we use the same thing. So we use machine learning to generate cloud maps at like regular intervals and then interpolate it between those cloud maps. Cloud map is the condition of clouds in sky at a point of time in 2D. And you evolve that using machine learning, basically.
So is it like a 3D scale?
It's like a 2D map of clouds in the sky. Okay.
So the one on the right,
Yeah.
rendered using the cloud map, right? Or is this
So cloud
rendering
map.
also that also follow?
So GAN is only producing the cloud maps, and then we put it in our renderer, and because we want to have real-time constraints, we want to have this happening in real time, and it was happening in real time because you just get a small cloud map from GAN, and that creates all this.
What does the cloud map store in terms of data?
It's only an image.
Okay, got it.
So, well, not very happy on where what it was published because we had some complications. It got accepted somewhere else and some major revision, and then eventually we wanted to just finish and publishing it. So we published it in Frontiers. Yeah. Yeah. So we generate this cloud map from the DC GAN, and we have trained it like that. So when we even train it on the cloud on the videos that we got from users, we extract it as cloud map and train it. And when we give some initial random cloud map, which is generated with some noise, it evolves that one. So each of these cloud maps is given to our renderer to generate into densities, proper densities that look like clouds. The,
Let's say the point cloud and the scale of the point cloud, let's say the distance of
One we generated like
Yes, that part is discussed in the paper that we have tried to keep it. I think it's uniform, and we have kept it at a reasonable interval so that we don't stretch it too much. That we do a recomputation before, and there's an interpolation involved here. So both the ways, right? So you need,
So you have a standard for the data.
yes, in a way. Does that answer the question? Yeah. So, but the idea was to see if AI can give you clouds, right? The answer was yes, it can. Yes. So I also wrote a survey paper on visual computer for cloud modeling, rendering, and animation. That was like four years ago, I think. And two more quick works, no slides, only videos. If you want to generate lightning bolts in images, so image to video problem basically. If you want to generate lightning bolt with the help of machine learning, that was another paper that we published in IPTA, Image Processing Theory Tools and Applications, IEEE. And do you think it looks real? It does, yeah. For machine learning and we had very less data because we had only few videos available online that gave us clear, single lightning bolts basically. So it could generate lightning bolts with that. Finally, we had a paper also last year in exploring the effects of four-weighted rendering. You know what four-weighted rendering is? So have you tried this headsets, virtual reality headsets?
Yeah.
So instead of rendering everything at the full resolution, you just pick up the central part. You see the central part and the peripheral region. So the central part is rendered at the full resolution and the peripheral part is reduced in resolution to save on the computation. So my student developed a simple game and did a user study because we do a lot of user studies to see if, because person shooter game is the most dynamic game. A lot of things change, right? Things are very quick. So to see the effect, if forwarded rendering would show any side effects if implemented in a first person shooter game. So this was published in IEEE Game Entertainment and Multimedia last year. That was for the research. I will not have any more research slides. But a few years ago, 3 years ago, we got a KK profile project. I'm not the leader. Veronica Sundstedt is leading this project. I'm leading theme B, which is about novel virtual environments. IKEA comes from Sweden. So if you look at their, shopping interface, if you look at their shopping, portal. So one possibility is that you're able to customize the furnitures on your own, right? To see, because if you want to buy and if you cannot go and look every piece because IKEA is maybe 100 kilometers away, so you would like to try it out, how will it fit in your room, what furniture arrangement you want. And plus you might also like to use headsets to see, to get the virtual reality feeling inside it. So this theme is most connected to IKEA, the theme that I'm leading, theme B. It's about novel virtual environments and interaction mechanism in the virtual environments, but it's a big project. There is my theme, then there is a visualization theme, then there is a networking theme, there's an AI theme, and there's a user experience theme. And many people are working on it. So it was about 90 million SEK that we got for this project. And yes, this is a very open thing, and I would like to collaborate with IISc. It'll be a great thing to do some things together. Could be at various levels. The idea is to get some high quality research, which you're already doing, but to be done jointly. We could write joint funding proposals. We could have visiting PhD students to Sweden, and we can also have some theses that are jointly supervised. Yes, and any other suggestions that you have. That is all from me. Thank you very much, and I'm open to your questions now. Thank you.
So usually when people want to do snow rendering, they don't use particles, like especially physically based particles, or perform any kind of particle interactive tests because that's expensive, right? So usually, I mean, usually people try to do even more hacky things.
It's called procedural methods, like the games that I was showing you.
Yeah. So my question is like, um, is the interest in particle? Yeah, actually, I've not understood this. Why do we venture into particle-based methods?
It's not about particles, it's about physics,
right.
right? So the existing methods are not physics-based, they're procedural.
Yeah.
They take a mesh, 2D mesh, they deform the mesh
Yeah.
to give you the impression that it's snow, right? But you cannot get all the effects, and plus it's actually not physically correct all the time, right? So the idea is that there should be physics for it, but the contradiction is that physics is so expensive that you cannot have for it. So any method that uses physics and can give you snow simulation at a good frame rate is the preference. But due to absence of that, people use procedural methods. So particles is only one way of doing that physics, right? The other way is grids.
Yeah.
And the benefit of particles is that there are some effects like splashes, right? These are very hard to create with grids because grids are working at grid levels, and no matter how fine your grid is, it's not easy to get a lot of splashes. You have to do that as a post-processing step. But with particles, you get splashes anyway. Yes. So these are the benefits of particles, and particles are very simple. If you understand the whole dynamics, and it's much easier to extend it, to implement it, to test it.
Is there a case where, and I ask this from a game design perspective, is there a case where you'd exclusively require a more particle-based approach rather than just, for example, for a splash, yeah, you can just use a shader or a post-processing effect rather than
But it would not appear realistic. You will pre-compute and keep like 10 versions, and then you will try to put them together to adapt to your situations. It will not look that realistic.
Oh, okay. So yeah, but so I assume then that this exclusively applies to places where you just want that level of realism. So maybe it's in the context of.
I think all games are turning more realistic, right? If you look at how skin looked in games 15 years ago and how it looks with all subsurface scattering and all, those operations were formidable. They could not be done on GPU 15 years ago, but now their characters are becoming more and more realistic. Same with any material that they use. They would like ideally that it would be a quantum computer, generating everything in real time or with all the nice effects. But as of now, it's not possible. So slowly components are being replaced with physics or with more realistic values.
Sure, but I'd assume the largest application here would probably be like places where it's just a lot more desirable to have a more particle-based system.
It's not about particle, it's about physics.
Physically
Yes.
based system.
Yes, exactly. But I mean, that's the reason why it got accepted in a few places because they felt that this requires some attention, basically, right? This work needs to be extended, and it's also on my list. I'm also working on it.
Have you looked at sand?
So the new framework that we are developing should work both and maybe for more materials. So we can mix. That's our vision, to mix sand and snow. Maybe it mixes somewhere in the world, but we will mix it.
Questions? I have a follow-up on that. So physics is, I mean, you made a case for physics. So to what extent are these representations, at what extent do these representations support high quality lighting that you want to bring in, right? So I didn't see the connection yet. I mean, I saw how the physics can be improved, how the different like all the aspects where physics.
Right. So there are two steps in all these simulations. One is the simulation itself, and one is the rendering. So you do the simulation, you extract an isosurface, and then you send it to, and extraction of isosurface and creation of surface is sent to an existing like NVIDIA Flex or something, and you put some lights. So people who are working on, rendering, for them, it's a different problem, basically, how to make it more realistic, or if my simulation should follow certain patterns, so rendering could be improved. But usually, people who are doing animation, they are not really paying too much attention on rendering.
But rendering that like you mentioned skin, right? So similarly, you would need the volume
Right.
to have, especially given that snow is translucent and there is going to be a lot of internal reflection.
Ice is
and ice, especially translucent. So
I think this.
the volume representation is going to be key. Just extracting
Right.
surface may not be.
Sure, if you have to have transparency and translucency like with ice, you will need all those things. But for snow, which is mostly opaque, you can have mixture of snow and ice with some level of transparency. But for snow, I think we need more particles. The more the particles, the better the better the looks are. But because of opacity, rendering part is only minimal. But for ice, it will be very important.
I did see.
But
Maybe it's a topic for discussion because I did see the difference between the images of snow and the simulations, at least in terms of the lighting,
Right.
the physics I could see.
Okay. Uh-huh.
But you talked about physics going from particle systems to physics. I guess neural representations are the way people are going, which brings in everything. So maybe that kills everything. Is that what's your take on it? A neural representation for
physics?
snow. Yeah.
So there was a paper like 3 or 4 years ago. It's about machine learning the simulation itself. So in material sciences, you have cases where one simulation runs for months because they are very expensive, right? So this particular cyclic neural network, I forget the name of that paper, but that one does exactly the same. So you like train it on simulations and then again give them the particles, and then simulation takes over, and it does it on a much lesser time than the simulation itself. But now we are dealing with 30 to 50 FPS already, 30 to 60 FPS.
The lights, all lighting, everything.
Mm-hmm. Well, you think that we could be?
I don't know. I don't work on neural networks at all. So it was more a question rather than.
Yeah, I had the same thought. How can I use AI for snow? Because I call myself an applied AI guy, and I think I would like to discuss this with you also. Maybe there's a way to do it.
So, is there other applications outside of the gaming and the entertainment industry for this kind of?
Virtual simulators, like Volvo has this snow simulators. They have these vehicles that plow snow. In Sweden, in Europe, you need snow plowers, right?
Yeah.
But you don't let people drive them straight on. You first get them trained somewhere. So if you have a virtual simulator that can handle real-time snow, with a lot of particles, that will be really useful. I'm pretty sure they don't have it. So
But
Volvo,
that's still the visual aspect is what.
but I mean, conventionally, computer graphics always has a separation. Animation works separately and rendering works separately.
I guess my question was more directed towards we have an interest in material science, so I was thinking more along the lines of that civil engineers they have an interest in.
Right. Why not?
I gave time for everyone to think about questions.